Recently, biomedical engineers have been interested in regulating biological processes using thermal stimulation in the body. In order to facilitate temperature-sensitive biological processes and phenomena such as biotransport, neural stimulation, and protein folding, there is a need for localized heat delivery in order to avoid off-site activation and unwanted processes. In the past few decades, the application of nanomaterials in biomedical engineering has advanced. Nanomaterials, specifically gold nanoparticles, can undergo phenomena known as surface plasmon resonance. This phenomenon allows heat to be emitted from the surface of nanoparticles when exposed to certain wavelengths of electromagnetic radiation. Using this property of gold nanoparticles, can we provide localized heat delivery? Our hypothesis is that we can provide localized thermal stimulation at a micron scale level.
So our project was completed within 3 phases. So our first phase was the synthesis of gold nanoparticles. Our gold nanoparticles were synthesized using a method called the Turkovic method. So the Turkovic method calls for the reduction of gold salt with a reducing agent such as trisodium citrate dihydrate, which is the one we used for this experiment. So after our reaction, our objective was to synthesize 20 to 30 nanometer sized gold nanoparticles. So in order to confirm the geometry of these gold nanoparticles, we use a variety of characterization and imaging techniques. So we use UV-vis spectroscopy, dynamic light scattering, SEM, and TEM imaging. The second phase of our project was the fabrication of a nanoelectrode. So in order to control the location of our gold nanoparticles within an artificial biological environment that we created, we wanted to be able to control it on a substrate so that it can be controlled with a controller or a micromanipulator. So our gold nanoparticles were bind to a boron silicate micropipette, which was controlled by a micromanipulator, and then we were able to characterize our nanoelectrode using SEM imaging to confirm that our gold nanoparticles are attached to our micropipette. The final phase was the actual experimentation to observe thermal stimulation. So experiments were done in a patch count rig, which are usually used for electrophysiology experiments, but we were able to measure the temperature inside our biological environment. We recorded the temperature at various distances within 30 microns, and we exposed our nanoelectrode to green visible light, which lasted for 1, 2, 3, and 5 milliseconds to observe thermal stimulation. All the figures shown display our characterization and imaging of our gold nanoparticles and nanoelectrode. So, the top left image shows UV-vis spectroscopy data along with the image of our gold nanoparticle solution. The top right image displays the dynamic light scattering data from our analysis, which displays that our gold nanoparticle diameter is 28.5 nanometers with a standard deviation of 9 nanometers. The bottom 2 images are SEM followed by a TEM image of our free-floating gold nanoparticle solution. The bottom right image displays the nanoelectrode with the gold nanoparticles coated onto it. The bottom left-hand image displays the setup for our experiments. A laser fiber is aimed at a nanoelectrode to induce thermal stimulation, which is then measured by a recording electrode. The temperature profile over time was measured in the bottom right-hand figure. 1 millisecond pulses were induced and measured for on-surface 10 microns and 20 micron distances. Finally, the top right-hand image shows the max peak temperature for all distances from 0 to 30 microns for 1, 2, 3, and 5 millisecond pulses. It's interesting to note that the temperature profile decreases by as much as 40% from 0 to 30 microns.
From experimental results, we can see that for all pulse sizes, gold nanoparticles can induce significant temperature change in the local environment, allowing for temperature jumps as large as 30 degrees Celsius. Additionally, the results show that there is a significant change in temperature profile within just 30 microns. However, resolution within 5 microns is not clear. The experiments we conducted support our hypothesis that we are able to obtain micron-scale resolution heating in nanomaterials. For future work, our next step is to test the cytotoxicity of our nanoelectrode.